All right, welcome to this explainer. Today, we're going to dive into the world of real numbers. And trust me, this is the foundation for pretty much all the math you'll ever do.
So let's kick things off with a little riddle to get the gears turning. What do pizza, the temperature outside, and even your phone's screen all have in common? I'll give you a second to think about it. What's the one thing that connects them all?
Got it? Well, the answer is they all run on numbers. Seriously, from the fraction of that pizza you're about to eat to that negative temperature on a cold day, numbers are literally everywhere, making our world work.
All right, so to really get this, we're going to build our number system from the ground up. Think of it like a family tree, okay? We'll start with the most basic, the very first numbers we all learn as kids.
And that first branch on our tree? That's the natural numbers. These are your good old-fashioned counting numbers. 1, 2, 3, 4, one cookie, two friends. You get the idea. Super simple, right?
And this set works perfectly, until it doesn't. What happens when you have, say, 3 cookies and you eat all 3? How many are left? Suddenly, our natural numbers have a problem. There's no number for, well, nothing.
So to fix that, we had to literally invent a new number, 0. It was a huge deal. And once we add 0 to our collection of natural numbers, we get a new set called the whole numbers. Problem solved. Now we can talk about having nothing left.
Okay, so our number family is growing, but we're still missing a big piece of the puzzle. What about when you owe someone $5, or when the temperature drops below freezing? Our whole numbers can't handle that.
So we need to expand our toolkit again. This time we bring in the opposites of our counting numbers, the negatives. And when you put the negatives, 0, and the positives all together, bam! You get the integers. Now we're talking. We can represent debt, freezing temperatures, anything below sea level, the whole shebang.
All right, so far so good. We've been dealing with whole things, right? But life isn't always that neat. The world is full of pieces and parts, which brings us to our next big category, what I like to call the tidy numbers.
I mean, think about it. Integers are fantastic, but they can't help you describe that one slice of pizza we talked about, or half a cup of flour for a recipe. We need a way to handle these in-between values, these parts of a whole.
And that's where rational numbers come in. The name is a dead giveaway, right? Ratio now. A rational number is any number that you can write as a simple fraction, a ratio of 2 integers.
Now here's what might blow your mind a little. You'd be surprised how many numbers are actually in this club. Obviously, fractions like 1/2 or -3/4 are in. But guess what? So is the number 7, because you can just write it as 7/1. And what about decimals? Well, if a decimal stops, like 0.5, it's rational. And if it goes on forever, but in a repeating pattern, like 0.333, that's rational too. They can all be written as tidy little fractions.
Okay, so everything seems pretty neat and orderly, right? Rational numbers can all be put into these tidy little fraction boxes. But there's another kind of number out there, a wilder, more mysterious kind that just refuses to play by the rules.
Yep, these are the irrational numbers. Again, the name tells you everything. They are not rational. You can't write them as a simple fraction, no matter how hard you try. And when you look at them as a decimal, whoa, it's a wild ride that goes on forever and ever with no repeating pattern. Total chaos.
Let's make this super clear with an example. Take a rational number, like 3/4. As a decimal, that's 0.75. It stops. It's clean, it's tidy, it's done.
But then you have a celebrity number like pi. 3.1415, and so on. We need pi for everything from engineering to figuring out how much pizza is in a round box. But its decimal form just keeps going and going and going with no pattern forever. That, my friends, makes it a classic, card-carrying, irrational number.
Okay, so we've got these two totally different teams, right? Team Rational, who are all neat and tidy, and Team Irrational, the wild, unpredictable ones. So, how do we put them all together? What's the big picture?
Here's the most crucial thing to get. A number cannot be on both teams. It is either rational or it is irrational. There is absolutely no overlap. It's one or the other, period. They are completely separate categories.
So what happens when you take Team Rational and Team Irrational and combine them? You get the real numbers. This is the giant umbrella that covers everything we've talked about so far. The natural numbers, the integers, the fractions, and those crazy irrationals. They're all part of the real number family.
All right, now that we know all the players on the field, let's put this knowledge into practice. A really common thing you'll have to do is take a bunch of different numbers and put them in order.
Okay, let's say we have a little showdown. 2/3 versus 5/6. Which one's bigger? Well, comparing them like this is kind of tough. The trick is to find a common denominator. So let's turn 2/3 into 4/6. Now it's easy. 4/6 versus 5/6, no contest. 5/6 is bigger.
But what if you get a real mixed bag of numbers, like a fraction, a decimal, a square root, a negative number? It's a mess. The absolute key, the #1 strategy, is to convert them all to the same format. Decimals are usually your best bet. So you turn -5/2 into -2.5, the square root of 9 into 3, and pi into about 3.14. Now you can just look at the decimals and line them up from smallest to biggest. And don't forget this last step, it's super important. You write your final answer using the original numbers, just in the right order.
And that right there, that brings everything full circle. Think about a number line. Every single number we've discussed today, from simple whole numbers to negative fractions to a wild number like pi, every single one has a precise spot, a unique home on that line. If you can imagine pointing to any spot on that infinite line, you are pointing at a real number.
So, this whole journey through our number family tree, it's pretty amazing, right? It shows us this beautiful, huge, structured system. But it also leaves us with one last kind of spooky question to chew on. Think about it. If we have to go out of our way to call these real numbers, does that mean there are imaginary ones out there somewhere?